Well then, the arithmetical hierarchy. So we already know all the definitions involved essentially, right? We saw the sigma 0 n sets or relations. These are those ones which can be described by a formula that starts with an existential quantifier, has n plus 1 alternations between the quantifiers, and then has some computable property on the resulting things. We also saw pi 0 n, which is the same thing except that now you start with a universal quantifier. Then I have no recollection whether or not I already mentioned this, but there are these, what do you call them, ambiguous classes, the delta n, and those are the things which can be expressed both in a sigma n way and in a pi n way, or equivalently those are those sets which can be expressed in a sigma n way, and their complement can also be expressed in a sigma n way. And so in particular, you notice that if n is equal to 1, then we know something very interesting about this, because then you have the delta 0, 1 sets are those that can be expressed as sigma 1 and whose complements can be expressed as sigma 1. So then we have a theorem that tells us that these two things are the same. Right? If something can be expressed both sigma 1 and its complement is sigma 1, i.e. CE and its complement is CE, then the thing is computable. Which kind of, if you look at the title of this section, seems like a bad start. Because we collapsed part of the hierarchy just there. Oh, and I should say arithmetical is just the union overall and let's say sigma n pi n. And this is a very superfluous expression because we clearly don't need to pi n because pi n is contained in sigma n plus 1. Right? Any pi n expression you can put in front of it a dummy existential quantifier and you have a sigma n plus 1 expression. So if you take a union over all n, then you don't really need the pi n at all. So that's the hierarchy we're talking about. I guess the first thing to wonder is well, there's a couple of obvious questions you could have in mind now. If you don't yet, I hope you'll agree they're obvious after I put them in your mind. One, it says hierarchy. Is it a hierarchy, right? Do the sigma n sets, right? Sigma n, again, includes sigma n minus 1, because you can put dummy quantifiers in. Is this a hierarchy in the sense that these sets actually increase? Right? If they don't increase, then I shouldn't call it the hierarchy, then I should call it the theorem that proves it would be decollapsing theorem, right? It collapses everything together. Well, we want to show that it doesn't collapse. And we will be able to show that it doesn't collapse. The other thing we want to see is, okay, so then we get a hierarchy. What does it look like? Well, we have these sets, and then bigger sets, and bigger sets, and bigger sets, and bigger sets. And so now you can, if I give you a set of natural numbers, then you could say, okay, a way to describe how complicated this set of natural numbers is by putting it in the right place of the hierarchy. Right? Something is in sigma n but no lower, tells you something very deep and meaningful about that set, in principle. Right? You can express it in a certain way, you cannot express it more economically. So, are all sets of natural numbers measured here? Is there some restriction? Right? The question I'm asking is essentially, are these things is here? Did I just generate a uniform way of classifying all sets of natural numbers? And the answer is definitely no. The answer is definitely no for a reason, for if you think of the reason for seeing that not every set is computable, or at least the reason I have in mind, then the same reason applies here. Right? What's the reason I have in mind? There's only computably many Turing machines. So, countably many, yes. Both starts with a C. Close enough, right? There's only countably many Turing machines, so there's only countably many computable relations. Countably many computable sets, this is uncountable, therefore it's not the same. Now all we do is we have these countably many relations and we can put quantifier prefixes in front of them. But there is only countably many quantifier prefixes to put in them as well. So this is still a countable collection of things. Therefore, not all sets are measured, but for the purposes of this course, certainly the sets that fall out of this hierarchy are just complicated. Even though in other contexts there's plenty of sets out there which you would consider simple, in our current context anything which is outside of this is really just more complicated than we would like to deal with. Okay, so first things first, so I said one of the things that's going to matter is classifying sets in this hierarchy. Now, I'm not going to talk a lot about this. But how do you get a set into a particular sigma n? Well, you could do very creative kind of things, but the usual way is actually just to use the definition. Something is in sigma n if you can write down this expression. Now, usually the natural way to write down an expression is kind of complicated, and then you need to figure out, okay, I wrote this down, it contains 481 quantifiers, how can I collapse these things down? So there's a lot of quantifier manipulations you need to know, right? Some very simple ones, that if I have, there exists an x, there exists a z such that something happens. Well, the something that happens is computable, so in particular it can compute our pairing function and projection function, so you can collapse these two things in one existential quantifier which says there exists a pair such that something happens. In similar ways you can deal, well, if your quantifier is of the form there exists an x less than some given fixed number, then that's unbound. Like bounded quantifiers have no effect on this kind of thing at all. That's an intuitive, read the theorems in the book about it to see the exact meaning, but a bounded quantifier for this sort of analysis can essentially be ignored. So let's just do 1, 2, 3 of them, and we'll talk them through how you do this, and then we know half of how to classify something. Oh, I forgot something. So we have here, the superscripts here everywhere are 0. If you have something where you have a notation where in your context something is always the same, you might as well leave it out. Right? So the 0 is often left out. Sometimes in its place you stick an a set of natural numbers, and then you're talking about the exact same definitions, but instead of having the computable matrix in there, it's a computable. So that's exactly what you have here. Also, all of these things are light phase, and then bold phase is the union over all of these things for all you work with. Okay, so number 1. Fin is in sigma 02. So what is fin? Fin is that set of natural numbers that correspond to indices for Turing machines that are characteristic functions of finite sets. That are sigma 1 indices for finite sets. Okay, we know there is a difference between different indices, so I should be careful. Sigma 1 indices for finite sets. So that's to say, x is in fin if and only if wx is finite, right? Just what does it mean to be finite? Well, what it means to be finite is to say there exists an S such that, let me get the same expression as we have here, for every t wxs, for every t, wxs is equal to wxt, or t is less than or equal to s. And then you need to sit back for a moment and observe that this says exactly, there exists a stage S, such that in the standard enumeration of WS you're done with enumerating. Right? WXS is the elements in WXS are all the elements that will ever be there, because otherwise there is a bigger WXT which has changed. So saying that you only care about this for bigger ones is saying or it's less. I hope you'll trust me when I say that you should be able to write a Turing machine that checks this. Right. So that's also a computer. And this is really all there is to these kind of things. Right? Now, of course, your immediate question, which I'm not going to answer but the book answers, is
it computable?
Does it get better than this? Right? There's still an improvement before computable to be made, but did we just? Right? This was the first thing that came to mind. Are we just being dense that we can see how to do it better? You couldn't think about it a long time, but we need a strategy for answering that. Anyway, before we do that. Tot is in pi 0 2. So what is tot? X is in tot if and only if it means pi of x is total, right? Tot is the set of indices of total functions. And now again, you do not have to be very creative. If you know the definition of total, then you just stick it in there, and you see, okay, what should it mean? Well, for every z, phi of x, z false.
So there exists an x, or an s, and what you call
Exactly,
S.
right? There exists an s such that this holds in that many steps, and now this is good enough, right? Before we had the s in here, we had a nice criterion here, but it was not a computable criterion. By sticking in the S, you now have a computable criterion, and so essentially doing no work, just following the definitions, you've stuck tot into the hierarchy. Now, possibly you stuck it in a really crappy place, right? Maybe it's computable, it's not, but at this point you don't know yet. Maybe it's just that we're being too stupid to find a better expression. It gets closer to that when you start thinking about more complicated sets. Recursive. So what's recursive? What's rec? I guess now to complete the name change from recursion theory to computability theory, we should really call this comp. But so x is in rec if and only if Wx is computable, and now it starts being that you have different ways of trying to go about it. But the theorem that we just wrote to mind tells us that, well, this is the same as there exists a y such that Wx intersect Wy is empty, and Wx union Wy is a set of all natural numbers. Right? A set is computable exactly if a CE set is computable if its complement is CE as well. But of of course we have other theorems as well, and so in particular when you do this, we just applied some theorem we know about this. Maybe the result we get is suboptimal because we used the wrong theorem. Anyway, this happens if and only if there exists a y such that how did I write this down? For every n, for every s, n is in w x s implies n is not in w y s, and for every n there exists an s such that n is in w x s or n is in w y s. Right, this expresses exactly what you want. For every natural number at any stage, if this number has appeared in the x enumeration by this stage, then it has not yet appeared in the y enumeration of the stage. That's this first thing. So that expresses exactly the third disjoint, as C says. And the second one says, for any natural number there exists a stage such that this number has been enumerated into one of the two C's. So that exactly expresses that the union is full of omega. And so this now is the first time where you actually have to do some quantifier manipulations, right? Because if you do it the wrong way would be to say, okay, if I have a conjunction and some quantifiers in front, I can pull them out, and then afterwards I pull these out. And if you do it like that, then you get there exists for all, which is sigma 4, if I read it right. Of course, before you do that, you need to rename your bound variables, because otherwise things are going to go hopelessly wrong. But if you do it the other way around, first pull out these, then pull out these, you get there exists for all, there exists. The for alls collapse, therefore there exists for all, there exists, sigma 3. Oh, there exists for all, there exists over something which is clearly computable, therefore sigma 0, 3. Oops. Good. Okay. So then these are just examples, right? Any notion you could care about, apply some definitions, apply some theorems, knock about with the quantifiers, and you can at least stick it somewhere in the hierarchy. Right? It's not true for everything, because there's lots of sets of neutrals not in there. But almost anything you will care about in this course, if you define the set associated to it, apply the definitions, and you stick it somewhere in the hierarchy, and then okay. So now we want to work towards seeing that the hierarchy is a hierarchy. The first definition to make for that is to say A is sigma n complete if A is sigma n, right? We don't want to arbitrarily complicate. Sigma n complete should mean you're in sigma n. And the other statement should say A is sigma n hard in the right way, and that's to say, and for all B in sigma n, B one reduces to A. And then you wonder for a moment and realize that I have often said, right, in this course, it is really Turing reduction we care about. Turing reduction corresponds to this really nice intuition of information content. One reduction is just a interesting technical device which sometimes helps us out, but here it's very important that you take one reduction. Right? Well, it's important if you're willing for the moment to believe that a hierarchy is a hierarchy, then not all sigma n sets are pi n sets. Right? If you take a sigma n set, its complement is a pi n set by just quantifier, what are they called? The Morgan's laws. The negation of an existential quantifier is the universal quantifier of the negation. So all of the quantifiers flip. So we certainly couldn't have, if the hierarchy is real, we couldn't have Turing reduction here, because then any set reduces to its complement, and then sigma n sets should reduce to pi n sets, and pi n sets to sigma n sets, and the notion of completeness would, if existed, imply the hierarchy at least collapses widthwise, not necessarily height-wise, but it collapses widthwise, and that doesn't happen. Now you could say, okay, you just ruined my dreams of Turing reduction, so why should one reduction be enough? Well, one reduction is enough because if you have this sort of expression, lots of quantifiers are x describing a set, then if you reduce to this set in a one or many one way, one of the exercises asks you to prove that I could have put many one reduction here as well. If I now have a function f which one reduces to it, then just sticking in the function here on the parameters still leads to something computable. And so that shows that something which one reduces to a sigma n set is sigma n. And so at least the notion of sigma n completeness hasn't failed a priori yet. And after we see post theorem, we see that it works. Right, but that's the reason for one reduction here. Even though in general we really care about Turing reduction, but here I think I've argued that after I show you post theorem, you would agree that this is the right notion. Turing reduction would ruin it all. Everybody happy with this so far? Okay then. Post theorem. First item. I'm not going to go through the whole proof of this theorem, because part of the proof of this theorem is mucking about with quantifiers, and for me, standing here mucking about with quantifiers is just about as painful as you sitting there watching me do it. So I'm not going to do that. You make the right observations. Anyway, B is in sigma 0 and plus 1 if and only if B is CE in some pi n set. I guess I should be somewhat consistent about putting in the zeros or not. Let's go for not. Right? And now, of course, equivalently, B is CE in some sigma n set, because if you're CE in a pi n set, then you're also CE in its complement. Every oracle question you ask, you just negate the answer you get. So, okay, so you look at this, and for a moment there, you should have the idea that this is absolutely obvious. Why is this absolutely obvious? Right? Set n equal to 0, then it's a case we know, because if n is equal to 0, it says the set is CE if it's CE in some computable set. And if you're CE in some computable set, you're CE. Right? So that's the n equal to 0 case. And now half of this immediately remains if we increase n. If you're sigma n plus 1, then you can be described of the form there exists an x such that, well, look at the such that expression, that's exactly a pi n expression. So your sigma n, your sigma 1 in this pi n expression, which gives you exactly according to the theorem we had before, your CE in some pi n. Right? notice that that is exactly the proof that works for 0. If n is equal to 0, then that's sort of the proof you use for that direction. The other direction is a little bit more involved, because right, if you're CE in some computable set, the computable questions are really no questions at all, right? So you're not asking any questions, so then you're really sigma 1. But if you are asking an arbitrary number of questions and asking about their answers, then this is a lot more complicated. This is kind of related to this idea here, right? You can stick in the f and you still are computable, but you cannot stick in the f, use positive and negative versions of the questions, and expect to still have the same kind of thing. Right? If you have something which really is sigma n, and you use this as an oracle, I guess pi n, if you use this as an oracle for both positive and negative questions, well, the positive questions are still pi n, the negative questions became sigma n. And so somehow you have to deal with the fact that the questions you ask your oracle here are both pi n and sigma n. Why does it work out? Well, because if you have some expression that is pi n or sigma, or sigma n, this a priori is pi n plus 1 or sigma n plus 1, and so then if you do that, but now we put one more existential quantifier over it, and then this top existential quantifier can be absorbed into this one, and now you have pi n or pi n plus 1 minus 1, which is pi n, and now you have one existential over expression like that. Now you need a couple more details, right? There is a bounded quantifier in there to indicate that things work out for an initial segment of your oracle questions, but this is sort of the essential idea why it works. Your questions go both ways, so a priori you have a problem, but you have an existential quantifier around to absorb the problem, and the problem disappears. You're all good. Jump of 0 is sigma n complete. Well, as soon as n is greater than 0. So with this we're in business, right? Because it happens to be that we know something about the sequence of jumps. The sequence of jumps is strictly increasing in Turing degrees. Therefore, certainly also strictly increasing in terms of 1 degrees. Right? The nth jump does not Turing redone. The n plus first jump does not Turing reduce to the nth jump. Therefore, it certainly doesn't 1 reduce to the nth jump. So this seems to go in the right way. That we can place these things in the hierarchy, and we know these things are really different in a way that we care about. So this should be the fact that implies the hierarchy is interesting. Okay, how do you do this? Well, of course, when n is 1, we've already proved this, right? The halting problem is 1 complete for all CE sets. So that's the base case. And then you just do induction. So the induction step, I wrote down the sequence of equivalences. If B is in sigma n plus 1, we would like to see that B 1 reduces to, and yes, plus 1. So B needs to 1 reduce to the n plus first jump. This is exactly what I have in my notes, which is fortunate. So if this happens, well, we know this means exactly that B is CE in a sigma n set, But I didn't write it, but I observed it. If you see it in a pi n, then you also see it in its complement, which is sigma n. So your CE in some sigma n set. By induction hypothesis, 0n is sigma n complete. So wherever you can use any sigma n oracle, you could use the nth jump. So this means that B is CE in 0 jump. But this kind of expression we've seen before, being CE in some jump, according to the jump theorem, appropriately named, it analyzes what happens throughout the jump. If you're CE in some set, then you one reduce to the jump of that set. So this exactly says that B one reduces to n plus 1. And again, at the time, when we proved the jump theorem, we did notice that one reduction is exactly the right kind of thing, and here it kind of meshes up, right? It's somewhat. This is what you need here to get that theorem, according to our definition over there. Okay. So from this, everybody happy with this one? We can see that B is sigma n plus 1 if and only if B is CE in the nth jump. There's not really much to observe. Just combine the first two facts here. This one is complete. If you're in there, you're CE in that kind of set. So if you're CE in that kind of set, you're also CE in that kind of complete set. And finally, B is in delta 0 n plus 1 if and only if B Turing reduces to the nth jump. And this is really nice because we kind of felt that the one reduction was a little irritating everywhere because we like Turing reduction better. So this at least tells us how Turing reduction behaves in this context. If you Turing reduce to 0 n, then you're delta n plus 1. And the proof is really easy. Delta n plus being in delta n plus 1, what does it mean? You're both sigma n and your complement is sigma n plus 1. Right? This is per definition. This means, according to the previous item, that both you and your complement are CE in 0 in the nth jump. And now we use the right version of the complementation theorem, relativized complementation theorem. And this says, right, if you and your complement are CE, then you're computable. If you and your complement are CE in some oracle, then you're computable in that oracle. And that says exactly that you Turing reduce to 0 n. And all of these are equivalences. So we really managed to put our finger on where this lives. Okay, wonderful. So what do we have? We have a real hierarchy, as witnessed by the jumps, which really increase, and therefore the hierarchy does not collapse. We have a strategy for showing things are somewhere in the hierarchy. And then of course comes the hard part in general, to show that, okay, something is somewhere in the hierarchy. It doesn't get any better than that. I say the hard part, of course, sometimes it's extraordinarily difficult to write down a simple expression for something, but you should hope you write down something reasonable. You can either try and write down something simpler that's reasonable, or prove that you've done as good as you can. So I just want to do one proof that shows that something is as good as it gets. But I suspect I won't finish. Then I'll try to at least say enough useful things about it, so that we can make a running start next time. So of course there's lots of choices. Which theorem to pick, and I picked this one because it involves a nice kind of construction. This is often a theme that I pick stuff with, not because they themselves are the most interesting result, but because they're good illustrations of a method. And then, if you feel like it, you can read the other constructions using the same wonderful method yourself. Anyway, so this is COF is sigma 3 complete. So what's COF? This is the collection of cofinite sets, right? Those CE sets whose complement is finite. So this means X is in COF if and only if Wx complement is finite. That's just a definition. I haven't done anything. What does it mean for the complement to be finite? Well, it means that there exists some bound such that if you're above this bound, you're in the set. Right? So if I set that right, then it corresponds exactly to this expression. There exists a y such that for every z, either z is less than or equal to y, or z is in Wx. Right? From y on, everything is in Wx. And then you say, okay, this looks sigma 2, but this is not yet computable. How do you make x's in W computable? Well, you put in an extra quantifier. So this says there exists a y such that for all z that exists in S, z is less than or equal to y, or z is in Wxs. And now we have a computable matrix, and over it we have there exists for all there exists. So we're in sigma 3, right? Halfway there. We're in sigma 3, now we need to be sigma 3 complete. Okay, so how do you show sigma 3 complete? Look at the definition, which I just erased. It says, take any other sigma 3 set. This any other sigma 3 set needs to 1 reduce to this one. So I take any A which is in sigma 3, and I want A 1 reduces to COF. Right, what does it mean? What it means is, for any x in A, I need to find an fx such that W of fx is cofinite. That was only one of the implications, right? Where I said if, you should have heard if and only if. Right? You're in A if and only if this WF of x is cofinite. Now, okay, I'll just describe part of the construction. I can't quite completely finish it. But the idea is as follows. We're going to come up with a set B, which is CE. We're going to somehow construct this one. And then what we're going to try and get for this B is that x is in A if and only if B super x is in COF. B super x is like the xth column of B, right? Pretend all natural number, right? The natural numbers is the same as the pairs of natural numbers, and so B super x is all pairs of natural numbers whose first coordinate is in x. That's not quite right. y in n such that there exists an x in n such that x comma y is in B. If that's what I said it right. Otherwise, I said it right now. Right? This is all those things in B whose first coordinate is x. It's the second coordinates of all those things in B whose first coordinate is x. That definitely is. Right? I'm just reading what it says now.
So, but the way you wrote just doesn't depend on x. So maybe there depends.
What do you mean it doesn't on x?
The set that you wrote down is just a projection on the second
Oh.
coordinate.
There you go.
Exactly, right? What I said. I guess the comment I said, what I said might be wrong, what I wrote is right, it was not right. But this is pretty sure. You all agree? Or
Well, we don't know what you're talking about.
okay. I put my foot down, this is it. If it's not, I'll secretly introduce a different notation next lecture and pretend it never happened. So this is what we want. And this clearly gives us a nice uniform way of doing it. Right? You have this one CE set, and the question, is the xth column of this CE set cofinite? Right? What is the size of the xth column? Is a 1-1 question. For different columns you're asking a different question, so this would give rise to one reduction. How are we going to do this? Well, the most basic version of what we're going to do is just look at Bx complement at stage S. Right? You've done S things in your computation. Oh, I should say, of course, we're trying to build a CE set now. So if you're doing a CE set, then of course it needs to look like go along doing computable stuff, and every now and then say this goes into B. Compute some more stuff, this goes into B. Compute some more stuff, this goes into B. So that's the construction we want. The way we're going to do it is at stage S we have enumerated a finite part of B. Right? That's finitely made. In time S you cannot more than S times say and stick this into B. So at stage S we look at this complement, and this complement is a cofinite set. But in particular we can write down this thing in some increasing enumeration. Right, now I might say, okay, it's a little suspicious because we have a finite set, but do we really know what this finite set looks like? Well, yes, you know exactly what this finite set is because you were the one enumerating the finite set. Right? So you really have, if you have a canonical index, then you can write this down effectively as well. In particular, well, also it looks like there's infinitely much information here, but I said B is finite, therefore the xth column of B is finite, therefore right, from some point on it's just all numbers. So these are to be thought of as markers lying on the complement, and we're going to keep them in order. So if I do something to B1, then the marker B2 will always be marking an element bigger than the marker B1. These are just, imagine you're playing a game, and you have these markers, and sometimes you just slide some markers around. Also what we're going to do is we're going to take these markers and only slide them up. Right, so if I say slide up B1, what does it mean? Well, B1 goes to position B2, B2 goes to position B3, and everything slides over by 1. Now, what is the observation that's going to make this useful for us? To be cofinite means that this complement should eventually be finite. Right? What is one way you can make sure that a complement like this is eventually finite? Well, if, for instance, B1 infinitely often moves over. If B1 infinitely often moves over, then none of these markers can stay in place, and so all of them kind of slide off to infinity and disappear. So there is only a finite part that's left of the first marker that moves infinitely much, those things stay in place. So there's finitely markers that mark the whole complement, therefore the whole complement is finite. If on the other hand, there is no marker that moves infinitely much, right, the exact negation of what I just said, then every marker comes to a rest somewhere. And if every marker comes to a rest somewhere, then the eventual complement is infinite. So we exactly have if we do this construction like this, you're in conf if and only if there exists a marker that moves infinitely much. And so now we just need to come up with a strategy that we can do. Go along, compute some stuff, decide to move a marker. Go along, compute some stuff, decide to move a marker, and do this in such a way that this happens for that A. That's going to be the trick. But, this is the basic construction. Surprisingly enough named the movable marker construction.